All right, welcome to my book lecture series. We're starting chapter 3. So this will be section 3.1, functions. Elsewhere, I uploaded a video on the 5 levels of understanding a function. I might refer to that here and there in this video. Won't kind of go over that same idea, but some of the ideas will be familiar. So the objectives of this, first they start with a relation. Certain special relations are functions, and we deal with functions. So that's really an important idea, is which relations represent functions. Use function notation, find the value of a function. The difference quotient, it's a popular idea in calculus. A lot of times this class is kind of viewed as one of the stepping stones to calculus, and so there's this kind of spillover, I guess, where they teach us the difference quotient. You will want to know what it is, though, even in this class. Find the domain of a function defined by an equation, all right? And then you can add, subtract, multiply, or divide two or more functions. So there's a lot to cover in this section. It's a fairly, probably one of the longest sections in the first half of the book, I'll say. So they define a function. Let x and y be two non-empty sets. The function takes values from x and calculates values of y. I don't want to read that directly, but you can read the formal definitions of a function. But I do want to get to some examples here. If I harp on every sentence here, I'd just be reading this to you, and it'd be a very long video. All right, so you'll see illustrations like this, and I just want to let you know that that's kind of the idea of the table. Let's say I have a function in my mind. I'm not going to tell you what it is, but it's a function that when you put in 0, you get 0. When you put in 1, you get 2. When you put in 2, you get 4. When you put in 3, you get 6. And even though I didn't tell you what the function is, I've created enough that you might know what function I'm talking about in terms of an equation. But I'm not talking about equations right now. I'm talking about the fact that we can think of anything I put in here as the domain and everything I put here as the range. And one way to describe a function is with a table. And when I say you probably have figured that out, that's also most likely the function y equals 2x. I might need more examples to really convince myself that that's the function. But I just want you to know that there are multiple ways to talk about a function. Equation is just one of them. Table's another. And they kind of made the table an abstract diagram in here because they're not trying to emphasize the actual function. They're just trying to emphasize that you take x values and the function gives you y values, called the range. And the x values are called the domain. So they want you to determine if an equation, so they is a function. So they changed from these kind of blob, abstract diagrams, bypass the idea of table altogether. They're already to the idea of an equation. So this is a good example. Basically what you're looking for is, if I were to put any allowable value of x, would I get 2 answers for y or just 1? 0 is okay as well. I mean, if I could put a value in for x that didn't work, that's okay. But is there any situation where I'd get 2 values? Well, think about it. If you give me a number and I multiply it by 3 and add 7, there's only one answer to that question. And so basically that's the idea. For one input x, you get one output value y. It's the idea that you get one answer, not 2. Now, I like to give an example of a calculator. If I were to actually hit the buttons on a calculator, in a problem like this, where I took a number like 5, multiplied it by 3, then I added 7, and I get an answer. That's got a decimal in there, but you might not be able to see, but it gave me an answer. But it gave me one answer, and that's the whole point. Calculations of a function should give us one answer. Let's see a function that's, or an equation that's not a function. So take this problem. So this one, it's asking, is this a function of y as a function of x? So that's very important that we get our variables kind of squared away on this. Is it a function in that case? So all they did was they solved for y, and the process, especially this last step in the process, the square root property, where if you have y squared or a variable squared equals something, you could take the square, but you have to tack on the plus or minus. So if you do this properly, you get this plus or minus, which suggests that this is not a function, because if I put in a number that works, let's say I put in 0. Actually, I'll go ahead and do that in a second here. They do that on this slide. If I put in 0, I'll get 2 answers. Well, I thought they did it here. Oh, it's on the slide. All right. You get 2 answers because of the plus or minus that was required from the process. So that's a situation where you put in one value of x, you get 2 answers for y, so it's not a function. It's still something. It's still a relation that relates x and y, but it's not a function, and we sometimes deal with, more often than not, we deal with functions. All right, function notation is all over the place. I think you've been exposed to it. Instead of just saying y equals, say, 2x plus 5, we can say f of x equals 2x minus 5. I said plus 2x minus 5 because it helps with calculations like these. So that's function notation. I kind of like these little illustrations here. It kind of gives you an idea for a function. Remember that function I had, the doubling function? If I said y equals 2x, right? Or f of x equals 2x. So if I put in a 3, what's going to happen is I'm not going to get 2 answers coming out. I'm not going to get 6 or 10, something like that. That just doesn't make any sense. If I know what this function does, and I know it's a function, I'm just going to get one value out. So you put in a value and get one value out. That is a function. What you put in are the domain, and what you get out are the range. All right. So lots of ways to visualize what we're doing here. They do talk about independent variable. That would be x, because that's the value that you're putting in, and you can pick it. And y is the dependent variable because you don't get to pick y, you calculate y. And I definitely like the idea of this word here. I use it a lot. The independent variable is also called the argument of the function. Anything you put in here is called the argument of the function. So for now it's x. But if I put something bigger than there, the whole expression would be the argument of the function. Now, I want you to understand that when you see this, what it's really saying is f of any argument is 2 times that argument squared minus 5 times that argument. And the reason why I want to emphasize that is students sometimes have trouble without verbalizing that. If you can say that, I think you'll do well on all of these, even the last few, which are the ones that generally cause students a problem. So let's look at the last 3 of these. So remember the way I'd written it was the function is f of any argument is 2 times that argument squared minus 5 times that argument. That's not the way it originally written. It was written f of x equals 2x squared minus 5x, but we know what it means. So what it means is if your argument is 2x, it's 2 times the argument squared minus 5 times the argument. Just going to say that as you're doing the substitutions. Simplify it, and we get an answer. Now, this is where students start having trouble. You could have had trouble earlier with, some of the algebra steps, but this is where students have trouble with the whole idea sometimes. If I say f of x plus 2, x plus 2 is the argument, so that's the whole thing. So it's going to be 2x plus 2 squared minus 5x plus 2. So whatever the argument is, that's what I have to do this to. So make sure you square it properly, distribute, and we do get an answer. F of x plus 2. It's got, when I say it, you can't really tell what I'm saying. If I say f of x plus 2, you might think I'm saying f of x parentheses plus 2. So f of the entire argument, x plus 2. Now this we're going to see again in the difference quotient, so make sure you get it now. What if I have f of, and the argument is x plus h? There is a technical way for me to read this. I can read this as f of the sum of x plus h. That's a little awkward, but especially if you're following along. So f of x plus h is 2 times the argument squared minus 5 times the argument. So you work it out and simplify it to the greatest extent that you can, and you have this entire expression. Now I'm not surprised that expression has 2 letters in it, because the argument had 2 letters in it, both x and h, and so you can see how they are all kind of meshed in there. Okay, important facts about functions. For each x in the domain of the function of f, there is exactly one image, f of x or y, in the range. However, more than one x in the domain can have the same image in the range. What that's saying is more than one y value, the y value can be the answer more than one time. We'll get to examples of that. The f symbol, so we use f, I won't read this to you, but we use f and letters of the alphabet around there, F, G, and H, and also capital letters like A, I've seen for area or amount, and T for, I don't know, time or something. If you see a capital letter, it usually is actually standing for something. F, G, and H are just the letters of the alphabet that we tend to use for functions. All right, now I'm going to get to the difference quotient. So let me kind of zoom this out here if I can. You have some questions that just specifically say find the difference quotient. So you are going to need to know this little formula, or at least have it written down. It's f of x plus h minus f of x all over h. And you have to simplify it as far as you can take it. So not only do you need to know what the difference quotient is, but you might get a little bit of a workout in simplifying. Shouldn't be any surprises on any of these. So here we're just writing down the formula. But by the way, we changed the function. It's now argument squared minus 1. If we tried it with that previous problem, it would have been pretty tedious because it was a lot harder. So they gave us a simpler function here. So this first part before the minus sign, argument squared minus 1, and then minus just f of x. So not minus just this exact x squared minus 1 over h. Simplify, and this typically happens, can't say it always happens, but it typically happens where you can factor out the h and cancel the h, and it's no longer a fraction. Still has both letters in it, x and h, maybe, but the simplification process is sometimes the biggest part of this whole thing. Look at one more here. F of x is 1 over x. And so if you did that, remember what this is saying. F of x is 1 over x. So f of any argument is 1 over the argument. I could just replace x with whatever the argument is. So if the argument is x plus h, this little piece right here will be 1 over x plus h. All right, the process of simplifying was just doing the subtraction, getting a common denominator. But notice how they did a lot of work. Eventually an h canceled, but not entirely. There was still an h and an x in the problem. Again, not unexpected. So to do one more, let me do one more. We still have other things. Like I said, this is a long section. All right, what if the function is 2 square root of x? Well, it's 2 square root of an argument. We're going to have 2 radical x plus h. Everything else cancels, simplifies as it does. And I noticed they did something a little unusual here. I don't even know that this was bad. Not sure why exactly they decided to, I guess, rationalize the numerator. Maybe they said something earlier, I don't know. For a lot of intents, this was fine. All of this other work really didn't simplify it and actually put a radical in the denominator. So I'm going to kind of call foul on this one and just say we could have stopped right here. And because there really was no more math we could have done reasonably with it. So this was one of those times when I think the author was just trying to show that he could do something and did it because he could, but it's a perfectly good answer. In fact, I think better answer than this one in some ways. Now in a calculus class, this one is better, and I'll go ahead and tell you why. So in a calculus class, there's always a part A and part B of the difference quotient. So part A is exactly what we do, and part B is let h equal 0. Pretty much always. Might be some exception to that. So what I'm saying is this was fine, but what the author is saying is, yeah, when you get to calculus, you won't be able to put h equals 0 because the denominator, h is the denominator all by itself. So in order for this part B to happen, the author is kind of going through it. He never tells you about part B because this isn't a calculus class, but I just wanted to explain that's why that craziness ensued on this one, because once you did all of that work, you really could let h equal 0 and you would get something that wouldn't have a division by 0 in it. So one of those things we get to do, but not yet. We're not there yet, not in calculus. I already talked about what the domain is. I'll go ahead and kind of go through, let me go through this list they gave us at the end. I'll scroll back to one or two of these, but here's the kind of the summary of the idea of finding the domain in the book. I'll start right here. If the equation has a denominator, solve denominator not equal to 0. So if the equation has a denominator, you just want to know when the denominator is not equal to 0, solve that, and that will tell you the points you exclude from the domain. If the equation has a radical with an even index, so square root or fourth root, and then I come here and say solve arguments greater than 0, which is kind of words they use, but just we want to get to the math here. So argument greater than 0, argument not equal to 0 for the two things that might jeopardize having the whole, might take away from the domain. All right, so let's look at this one. All right, so basically that's the argument, and you want to solve argument greater than or equal to 0, because if the argument is greater than 0, it fits in the domain of the function, the square root function. So that's exactly what the author did here. A few steps later, express the domain in both set notation and interval notation. It's fine with a fraction right there. All right. So we're completely ignoring the numerator. We're just saying, you know what? X squared minus 25 cannot equal 0 because the denominator cannot equal 0. Solving that. And I'm not sure what method they use. Let me go ahead and do that. I'm looking, but typically we solve something like this with factoring. X minus 5, X plus 5 not equal to 0. Some people think it looks a little unusual to do it with not equal to's, but I like to write it that way. So I get X not equal to 5, and X is not equal to negative 5, which should look familiar when you have done this with an equal sign instead of the not equal sign. But what I'm saying is the shortcut is just take the denominator, not equal to 0. When you don't have anything that will jeopardize the domain, like a division, we'll later find logarithms or something, we just know that the domain is all real numbers because there's really nothing I can't just square or add 1 to. So that's what they say. The domain is the set of all real numbers on a polynomial or something like that. Yeah, this video is running long, but we're still not done. They talk about the idea of adding, subtracting, dividing, multiplying functions. And all I want to say about this, I'll just get one example in maybe, but it's not the distributive property. If you're thinking, oh yeah, that's obvious, f plus g of x equals, what I would think, distribute the x, right? F minus g of x is f of x minus g of x. Well, this wouldn't work with numbers. If I had a product and I wouldn't distribute like this, but it does work with a function. It certainly wouldn't work here. If I had some number over number and a number here, I wouldn't multiply that number twice like it happens here. These aren't distributive property, they're definitions. The definition of f of g over x is f of x over g of x. And so knowing those, it doesn't take too long, but just make sure you get it. You get the idea. And like I said, I don't want to do a lot of these, but let's kind of just go to the end and look at this one. Kind of the medium hardest one. F times g of x, well, means f of x times g of x. And you'd have to look at I call this one kind of hard, but it's not. Just multiply them together. So that would be the answer to f of x, g of x. F of x times g of x. And notice this isn't too unusual at this level to, anytime you have a denominator, just kind of punctuate the domain. Just state it again, what the domain is. So I guess this one is probably the most involved. If I have the difference of two functions, and by the way, it does make a difference which one you have, which one they give you. They could have just as well given us g of x over h of x, or f of x, but f over g is what they gave us. Substitute, and this was just a process of how fractions work. Multiply by the reciprocal, and you'll get your function. Now keep in mind, there was a point when this was a 4-story building, so there was 1, 2, 3 division symbols. So there's 3 places where the denominator should not equal 0. What I'm saying here is, if I look under this line, I know that x cannot equal 4. And if I look under this line, x cannot equal 0. If I look under this line, x cannot equal -3. Now, I pointed out here because as you manipulate the problem, you no longer have those 4 divisions. Something happened when we multiplied by the reciprocal to get this. And so this doesn't have any, as many divisions as it once had. So if you look here for the domain, you're going to miss something. Notice how the domain tells you x cannot equal 0, x cannot equal 3. But notice how it says x cannot equal 4. That's because of the earlier step where 4 would have caused the division by 0. Looking here, it doesn't look like it would cause any problems because it's no longer in the denominator. But I think we say this a lot of times. You have to, when you're talking about the domain of a function, you got to look at its roots and you got to look at every step. And if there's ever a step in the process where a number is excluded, it stays excluded from the domain. All right, that is it for section 3.1. Like I warned you, this really is one of the longest sections in the entire book, certainly the first half of the book. So it needed the longest video. But that is section 3.1. See you in the next video.